let's talk about the pkexec vulnerability. Systems are being patched right now, so it's kind of a given that most systems you try this on, it won't work. For example, my system has been patched. It won't work on my system. Still, there are, I'm sure, many unpatched systems out there. Systems for which patching is difficult. Don't abuse this information. So I have explicitly left out a piece of information needed to make this work. Now, most of the stuff I tell you in this class can be exploited, and so this is really no different in that sense. If you can't figure this out and really want to know what I'm leaving out, ask me and I'll tell you. Just don't abuse this information. Okay? So in case you missed it, there is a serious vulnerability, a privilege escalation vulnerability in something called pkexec. It's part of something called PolicyKit. And we'll talk about what all that is in a bit, but I think it's worth noting the timeline. So back in November, an advisory was sent to Red Hat. About almost 2 months later, an advisory and patch was sent to OpenWall, and then a little over 2 months after the first advisory, there's finally a coordinated release date. So during that time, a lot of people know about this vulnerability, and with a little work can exploit it. So that's not a great situation, but that's the one that we're in. It takes time. This is not unusual. It takes time after you find a vulnerability to understand the scope of it, the impact of it, and to figure out what a response should be, and then to coordinate that response, right? You don't want this group over here patching and these other people over here are unpatched for a couple of days. You want to have a coordinated result where people can have the chance to all patch it more or less at the same time. I mentioned the CVE earlier. So previously on a slide, we showed a CVE number for this vulnerability. What was that? Well, the Common Vulnerabilities and Exposures is an international standard for naming vulnerabilities. So instead of saying, hey, that vulnerability where that button on the router, you push it, and then there's this negotiation, and there's a 5-digit and a 4-digit number, and you can guess one, and it tells you which one you've guessed wrong. No one's going to know what you're talking about. Well, some people will. Instead of that, you can just say vulnerability 17. How about that? Or vulnerability 17 in 2021. That is a good way to do it. Then everyone can know what you're talking about, and more importantly, they can know if it's been dealt with, if a particular supplier or vendor has dealt with it. You can look it up online and read about it. It's good stuff. So MITRE Corporation developed this Common Vulnerabilities and Exposures system. It's trademarked by them. And you can use the designation for this one, CVE 2021 4034, to look it up in various databases. There's a link to the NIST database. There's a CVE database. And you could look it up in Red Hat or Ubuntu or whoever's different databases to see if they have addressed it and patched it. So what's PolKit? I mentioned this PolicyKit. What is that? Well, it's a package specifically for privilege escalation. If you've ever had a dialog like the one on the right pop up saying, hey, I see that you're trying to run this super fancy piece of software like CAT as a super user, you need to authenticate. You're using the PolicyKit. It lets you become another user or become the super user and then execute a command. The most common use case is becoming the super user to do something potentially dangerous. And so an example using it is that line at the bottom, which is a very verbose way of doing sudo. Right, but it's essentially the same thing. In this case, I'm going to cat the Etsy shadow password file, which will let me see all the hashes in the password file, which is generally considered to not be a great thing to do. What's pkexec? Well, we just saw pkexec on that previous slide. It is the setuid program that runs to do this. What is a setuid program? That's a program that when it is run, it changes the effective user ID to the program's owner. And pkexec is owned by root. If we list it, we'll see that it's setuid. This little S right here, where the X would normally be, indicates that it's not just executable, it is also setuid. When you run it, it will run as if you were the root user. And if we do a file on it, we'll also see that it's setuid. There you go. Let's talk about a weakness, a vulnerability, and an exploit. A weakness in a system is just a point where the security is weak or poorly designed, maybe poorly executed, or it could be fragile. Right? It depends on some set of circumstances that might not be true or that could be changing. An example of this is I have my super secure secret facility and I use wooden frame doors. Well, those are weak. They're fine in a lot of contexts, but they're weak in this context because someone can walk up and kick it really hard and the wood can split and they can go in. That's not what I want, right? They've escalated their privilege by getting into a place they shouldn't be by exploiting this weakness. A vulnerability is a weakness that can be exploited by a threat actor to cross a privilege boundary within a system. And an exploit is the specific collection of tools and techniques and practices that when you combine with one or more vulnerabilities, lets that threat actor cross the privilege boundary within the system. Okay, I didn't mention computers anywhere in this because this applies to any old system, right? Systems have security and they can be more secure or less secure. They can have weaknesses, etc. If there's a weakness, it may or may not give rise to a vulnerability. You can have a weakness but not have a vulnerability. It may be that a vulnerability arises when you have several weaknesses that you can exploit in concert to do something. But you can't have a vulnerability without there being a chance to exploit it, right? That a vulnerability implies that there is both at least one weakness in the system and that there's an exploit. We already know pkexec has a vulnerability, so it's reasonable to ask, what are the weaknesses or what is the weakness in it? So, with that in mind, let's think about where weaknesses and vulnerabilities occur. And I've told you a couple of things about them. I've told you that they often occur at the seams, where one system or component interacts with another, or where there's a convention that is assumed but not enforced. Computers are full of both of these. Like they're built out of both of these. And so we can expect to find some vulnerabilities if we can look hard enough. So with those in mind, with all this in your brain right now, here is a snippet of the current source code on GitHub for pkexec. And we're going to pause here for a moment, like pause the video, and see if you can figure out what the weakness is. Because it's the code that has the weakness is on screen right now. And the weakness has been there for 12 years. So to take a look at this, see if you can spot the weakness, pause the video, and then we'll proceed. Okay, did you spot it? Did you spot the weakness? Suppose argc is 0. Now that's never going to happen, right? Because the first argument is always your program name. And so argc is always going to be at least 1. because you always have the program name. Your first actual argument comes at index 1, and if you had an actual argument at index 1, argc would be at least 2. Right? There's always this weird add 1 thing with argc. But what if it's 0? Well, suppose it's 0, then we come into this for loop and we don't execute it. Right? We don't execute it. And n stays 1. Can that happen? Well, how did argc get there? It got there because somebody filled in information and invoked this program. But what if they didn't fill this information in? What if they didn't provide the program name as the first argument? Can you even do that? Turns out you can. You can totally do that. So here's some code that does exactly that. It starts pkexec, and it starts it with an empty argument list. And there's the argument list. It just has the terminating null, which you have to have. And in this case, argc is going to be 0. So there you go. Totally doable. So what? It's 0. What does that mean? Well, the for loop is never going to run. So take a look at that. N is initialized to 1. We run while n is less than argc, but argc is 0, so we never run. And so when this loop gets done, n is 1. There's an assertion here to check the argument list to be sure it's null terminated. Our argument list is null terminated. We passed a null as the 0th element of that array, if you remember. So argv of 0 is in fact null, so that assertion is fine. What about this? What happens here? Well, we go and we duplicate argv of n, and we set that to be the path. What is argv of n? That's argv 1. Okay, what's argv 1, right? We already established that argc is 0, so there's nothing in here. So, I mean, argv of 0 is null, so what's argv of 1? Is it anything? Let's talk about how the operating system lays out the stack when the process starts, because that's going to answer our question. The operating system does a lot of stuff, which we'll talk about in later classes. It resets the floating point controller register, it sets up your stack, all that good stuff. And when it gets ready to start, the stack looks like this. So here down here is where RSP is pointing. That's the top of the stack. Up here is the top of memory. And you can see that the argument counts the first thing on the stack, followed by all of the arguments, argv 0, 1, 2, and so on, here on the stack, and then the terminating null to end the argument list. That's followed by the first environment assignment in envp 0, up through a terminating null for those. These are your environment variables, and they're passed to you on the stack. That's followed by auxiliary vectors. We'll talk about those at some point. Followed by other stuff. Okay. So what happens when argc is 0? Well, this is what happens. Here's argc, which is 0. Here's the terminating null for the argument list, which is empty. And so argv1 points here at the first environment variable assignment in envp 0. So now argv1 and envp 0 are synonyms. That's going to be important. So what's envp 0? The first environment variable that was passed to the executable. And if you start an executable, you can control the process environment variables. And we know you can because, for example, pkexec does that when it starts a program. Because pkexec is a setuid program, the dynamic linker scrubs the environment variables because there are some that can be exploited. Exploitable environment variables? Yes. For example, LD preload causes the system to load libraries from a particular path before it runs a program. And you could exploit that. You could set it to something that points to your own malicious libraries they get preloaded, and that's bad. An example of this is in the lecture. So that would be bad. So the dynamic linker removes exploitable environment variables from the set of environment variables before it invokes a program. So what happens? Well, we come in here and we stirdup argv1, which we know is the first environment variable pointer, which is not null, and so we don't do this. Instead, we come down here and we see if it starts with a slash. And if it doesn't, we invoke this gfind program and path, which goes and looks at the path environment variable and searches for the thing we just found as path. And if it finds it, it returns the complete path to us, and we then store that back in argv_in, which is argv1, which is the first environment variable. So think about this for a minute. I get the first environment variable. I see if it starts with a slash. If it doesn't, I try to find it as a program in the path. If I do find it, I take the complete path, now in S, and I set the first environment variable to that. Wow, this gives me a way to set an environment variable. There's some constraints on it. It has to be a program findable in the path. But I can certainly do all of that. Seems like that could be a bad thing. And in fact it is. There's a little bit of defensive programming in pkexec. This is another excerpt from pkexec, and I love the comment in here. So they go through and now save the environment variables we care about. Just save some of them. They scrub the environment variables in much the same way that the dynamic linker does. To qualify for the paranoid gold star, we validate the value of each environment variable passed through to avoid exploits. So there you go. Well, it's too late. The weakness has already happened. But how do we take advantage of this? Well, it turns out the way to take advantage of it is by exploiting a connection to another system, and that other system is the stuff that handles printing error messages, gprintError. Well, gprintError just prints an error message, right? That's fine. Nothing you can exploit there, is there? Well, when you print a message, the system wants to convert from the text it's given in UTF-8 to the appropriate character set for whatever display you're using. And it may not be UTF-8. It turns out there are places in the world where they use other alphabets, etc., and they don't necessarily find UTF-8 to be the convenient encoding for those. Right? On Windows, you might have UTF-16, for example. So, what if the char says not UTF-8? Well, it can be whatever we set it to. There's nothing special or exploitable about the character set. It's just the character set. So it's not a security risk, so no one scrubs that char set environment variable. So now we've got to go to the man pages. gprintError calls the icon open to convert from UTF-8 to the correct character set. And you can read about that here. Right, so here we go from one character set to another. And then if you go and look at the man page for iconv, we'll see that internally it needs to find converters. And the converters are little shared libraries. And it finds them by using gconv_path. But if I point gconv_path to a set of malicious converters, that could be really bad. Well, okay, we've thought of that. Right? We've thought of that. It's a known problem, and when you run a setuid program, the dynamic linker cleans up the environment variable to prevent this. So if there were potentially vulnerable gconv_path, it was removed by the dynamic linker before pkexec started. Great. Except that we can use our trick to add it back. Here's how that works. We create a folder with this weird name, gconv_path equal dot. That's the name of the folder. It's a perfectly fine folder name. We cause a folder with that name to be created. And we add a file. And I don't care what's in the file. It could be anything. We call it, let's call it in this case, friend. We need it to be executable so that it's found as an executable by pkexec, but you don't care what's in it. And we need to specify a char set. And we do that over here. So if you look over here, I've modified the little main program. I still have the empty argument list so that argc is 0. But now I have an environment, and the environment consists first of just friend by itself. And then I set path, this is my search path, equal to that. Right? Search path is a colon separated sequence of directories. And so it may look weird that there's two equals, but this equal is assigning to path, and this equal is just part of the first name on the path. And I set my char set to Wordle, which is one I made up because everyone's happy with Wordle these days, and so I figured I'll just use Wordle. And then I null terminate my environment list. And then I use exec VE, because I've got an environment, to start pkexec. And I give it my argument list and my environment list, and that's it. What happens when this occurs? Well, the path is constructed with envp0 equal friend, right? This is going to be the thing that it finds, right? argv0 is here, argv1 is going to be right here, and so it's going to find friend, and it's going to look in the search path specified by path, and it's going to find friend in this folder, and it's going to construct the complete path, which will look like this: gconv_path equal /friend. Now I have specified a search location to find the little char set converters, and I can put a malicious char set converter in the friend directory, and I'm good. Well, not good. You know what I mean. So we create a folder named friend. We can put our own gconv modules file in it. I just copied the system one over and stuck it in there, and then I added my little Wordle to it. And so we pop down here, and you can see right about where the cursor is. There's my little module to convert to and from the Wordle encoding. Great. So now I just need a malicious encoder. Well, that's the code over here on the right. So encoders have an init, an end, and then a conversion step. And my init doesn't do anything, my end doesn't do anything. I could have put all this code in init, and maybe that would have been better. I don't know that I care. It works. But you can see what I've done here. So down here, when you get to the conversion step, what I actually do is I start a bash shell as root. Right, I set my argument list equal to this. So look at that. There's the name, where it's supposed to be. There's null. My environment, I set my shell equal to bin bash. That'll be helpful. And then I set a path. It's nice to have a search path. And my path is user local sbin colon local bin, so on. The standard path that you get for root, just broken up into component strings so it fits on the slide, and then a null terminator. I do a set UID and set GID to 0. You need to do this, otherwise it will still be running as your real user ID. Remember, this is a set UID program, so you can start things as root, but that's your effective user address, not your effective user ID, not your real user ID. Your real user ID is still you, so you need to go ahead and make sure that you do these to set yourself to be root. Then you do an exec VE again with argv0, which is the thing you're starting, argv and envp. That starts the bash shell, and now I am root. Yay! I compile this, drop it in the friend folder. My modules file points to it, and life is good. Now, this is not going to work on my computer, and the reason is I've patched it. So instead of trying it out on my computer, well, we can try it on my computer. I've got it all built. Oops, I'm in the wrong folder. You'll get this. This is the symptom of it being patched. Let's head down here, and here I'm in a VirtualBox, and I have the same stuff here. So let's give it a try. So you can see I've got my Wordle.c and my startargv.c here. I've compiled them. There's my startargc executable. My Wordle shared object is now down in friend with the gconf modules. And there's my little path with friend in it. As I sit here and look at it, I realize I could have added a colon dot in here and put this stuff in the current directory, but you know, I can always make this better. Let's start it up, and I'm root. That's it. It's just that simple. So it's pretty easy to exploit. It's a little complicated to explain, but actually not as bad as some vulnerabilities. This took me a couple hours to build the exploit for this because I had to read up on. I didn't have one to work from. I don't know if there are any publicly published exploits for it yet, but at the time I was looking at this, which was last Thursday, there weren't. And it took me a little time to go and read about how icon works, but it's pretty straightforward. So this has been out there for 12 years. Are we really supposed to believe that nobody has ever thought of this? No, people have thought of this. Here's a blog post from December of 2013. And the author points out that most C programmers should be aware that the argv argument list domain is a null terminated list of strings where the first element is the name of the program. Yes, we all know that. There's an odd feature on Linux which allows the list to be empty. All right? By convention, the first entry is the name of the program, but it's not enforced. This allows us to execute an application with argv0 equal null. Many applications, including several setuid applications, make the assumption that it's always a valid pointer. I haven't found any exploits using this, but it does allow for some amusing behavior from setuid binaries. Oh my goodness. This was from 2013. Paulkit and pkexec were fairly new, so he may not have been able to find them right then, but there it was. That's it.